Okay, so this week there was a reference in the advertisement for the seminar. So this is non-locality as an information-theoretic resource. So some of the, most of the stuff that I'm going to talk about today is based on a paper from et al. From 2005, if memory serves. I want to make sure that I do this. Maybe 2004, sorry. Okay, and so last time, I just want to sort of recall what we... So last time what we kind of talked about was BilQC, and so the idea was you have some, so imagine that you have a circuit. I'm just going to do a simple little circuit. Maybe you have an entangling gate, and maybe you apply some sort of unitary on one, and then you measure this qubit, and you send the classical signal, which sends out an output M, to decide which unitary UM you might perform on the next qubit, and then you measure this one, and so on and so forth, right? So key here is, in order to actually perform the kinds of circuits that you want, you need to make sure that you measure, you send the result forward. So this has classical communication between, and I'm going to call these parties. So what you really have are qubits, and in BilQC, you have an array of different qubits that are spatially separated, and they're connected. So there's a classical communication that connects them, and all the measurements are local on each of the parties. So imagine that I do a version of BilQC in which I don't really talk about this. Now, you can't compute the same things. You can't do the same things, because key to what we wanted to do was you get the measurement outcome, you feed it forward, you do a different measurement, so on and so forth. But I want to consider a sort of simpler situation. Yes, Gian? Is it not working? Is it working? Is the audio working? Does somebody say it's not working? No, I was just checking on my phone. I couldn't hear it. I mentioned not. So you need to be unmuted on Zoom, right? I unmuted. Okay. Yeah, no, look, when I say something, the green goes up and down. It fluctuates. Okay. So this is the adaptive situation. And adaptivity means that there is communication. So I want to consider a simpler case where there is no communication, therefore there's also no adaptivity. And that would be a circuit that looks something just like the one that I wrote. However, or I mean similar at least. So suppose that there was some sort of, you know, this could be single qubit rotations, but also an entangling gate, just something a general unitary that in general in principle, could be entangling. And then you just do a measurement on each qubit, and you get a set of outcomes, A and B, and that's a piece of your statistics. So this scenario right here is going to be sort of like and I'll define what this is, Bell type measurement. Okay.
Is there any entanglement?
Yeah. In principle, it could. Of course, I just put a general U here. The U could not have any entangling gates, no C naught, no controlled Z. In which case, yes, you're going to get some measurement outcomes, but in general, they will not demonstrate significant correlations, like Bell-like correlations or something. Is that okay? Oh, sorry. Okay, so Bell / Okay, so I want to consider here a bipartite. Basically, when I think of a party, I think of the number of qubits, essentially. So bipart means I'm going to think of two parties. This is the sort of situation that we'll focus on mostly. And I want to draw a little picture of this. So imagine that you have these black boxes for parties Alice and Bob. And Alice takes some input, say X, and gets out an outcome A. And then maybe Bob takes an input Y. X and Y could be numbers. They're input bits, zeros and ones, something like this. And outputs a bit B. These could also be 0, 1, or we're going to see it could be 0, 1, 2, something like this. And I'm just going to, maybe this is not a good notation. I want to repeat this maybe many, many times. By the way, there's a distance. There's no communication between these parties. We can think of them as being space-like separated. The distance is greater than 1 in perhaps units where G equals H bar equals C equals 1. Then distance is unitless, so D greater than 1. When I repeat this n times, n much, much greater than 1, I get maybe a table, a bar graph of different outputs. Like this. So I want to think of these outputs as being like in the limit of n being very large. I can approximate the probabilities of this situation very well. And so I want to encode. So encode this scenario as. Okay, and the following picture is going to be a nice representation of what we have. In this case, say that we're dealing with just A and B being 2 bits. So I could have, here is Alice's side, here is Bob's side. I could have A equals 0, I could have A equals 1, I could have B equals 0, B equals 1. And so I can take here, I could have 0, 0, 0, 1. What is this? This is just the number of times Alice gets measurement outcome A, Bob gets B. They send it to some third party who just tabulates how many times these things happen. And so this is going to be like the probability 0, 0 of xy, probability 0, 1 of xy, probability 1, 0 xy, 1, 1 of xy. The fact that we are accumulating these probability distributions in a particular way means that we have a couple of observations. One is that because these are coming from recorded statistics, these numbers are positive or non-negative. So P, A, B, X, Y are greater than 0. And also, just by definition, if I do this n times, I can always divide by n so that these numbers sum to 1. A, B. So when we want to think about the relationship to quantum mechanics, basically, if I think of fixing a particular measurement basis, and then just I just perform those measurements on my qubit, different copies of the qubit many times, and then I get something that looks like this. So here's a particularly well-known scenario. Maybe I should write out the full name. Clauser, Horn, Shimoni, and Holt. This scenario, which also is just called CHSH, it consists of the following situation. It's this precise picture, but Alice could probably have one of two inputs, 0 and 1. Bob can have one of two inputs, 0 and 1. And also the outputs can be 0 or 1, 0 or 1. So the CHSH scenario is also called a Bell scenario with two parties, two inputs per party, and two outcomes per measurement or input. And so I want to basically encode this scenario in a box that looks sort of like this. So let's think about what that looks like. Okay. So again, I'm not going to label everything for all of these different choices, but I just will do, for example, this first box. Here you have A equals 0. A comment. So I'm going to do something a little bit, I'm going to be playing fast and loose. Sometimes I might want to specify the outcome corresponding to a particular measurement, in which case I might say that this is A0 equals 0, A0 equals 1, and B0 equals 0, B0 equals 1, and a similar sort of notation for these other ones. In the case where it's not going to be too important, I will just call them A and B, but sometimes I might want to be specific about the measurement outcome corresponding to a particular set of inputs, in which case I will reintroduce the subscript. So here I'm going to have basically one of these boxes for everything here. So this is P00, and this is the 00 input. I'll just put 00 rather than X0, X1. P01, 00, P10, 00, P11, 00, and then similarly just P maybe A0, B1 of 01, P. Actually, I might want to keep some of these. Sorry. Because I'll be talking about additional conditions. So these are two conditions that you get for just one box. Once you have more of these, there's additional conditions, and it will be good to actually have some of these written explicitly. So I will do P of 0, 0, P of 0, 0, 0, 1, 0, 1, P of 0, 0, 1, 0, P of, 1, 0, 0, 1, 1, 0, 1, 0, and this is just P, A1, B1, 1, 1. So here's the additional ingredient that we want to introduce in this sort of situation, which is the idea of non-signaling. Let's see. I don't want to go too far away, and I don't want to go back and forth too much. So maybe I will get rid of this. I don't think I need this. So this picture can actually just help us a good deal. And the idea is the following. Suppose that Alice and Bob are getting a bunch of inputs, and so what you would like is that if Alice or Bob randomly changes their input from 0 to 1, if all of a sudden the outputs that so say that Bob randomly changed all of his inputs from 0 to 1, and what you don't want to happen is that automatically Alice sees a change in her outcomes. Like Bob is doing something, he flips his switch, and then all of a sudden, simultaneously, in a well-defined sense, Alice also sees a change in her outputs. That's called signaling. So we want so there's a principle of no. And this is going to be basically a direct outgrowth of just making sure that your model is compatible with this theory of special relativity. In essence, you have two observers on a space-like surface. Sorry, this should probably be bigger. Where this is D. The theory of special relativity tells us that B can only affect something that's inside B's light cone. So B's light cone is going to go something like this. And so B should only be able to affect the outcomes of A after a certain amount of time has passed, so that a light ray could go from Bob and reach to the point where Alice would be forward in time. So we want to impose that this sort of thing happens, and this is going to be through no signaling conditions. So what do those look like? So maybe I'll just call them NS. And I'll do it, let's see, for this particular scenario. So what I'm basically saying is that so this is the distribution of outcomes that Alice sees. These are just the outcomes that she sees. And this needs to be the same as, let's make sure. Okay. Say I pick this to be a particular xi. So I sum over B, PAB of xi y0 equals sum over B, P of AB xi y1. So what is this saying? Irrespective of whether Bob chooses to measure in input 0 or input 1, the distribution of outcomes that Alice sees just on her own end are always going to be the same distribution of events. Is this okay? Maybe, I think a lot of people, through just popular culture, they're okay with this step. And there's a similar equation for Bob. P A B x0 yj equals sum a piece of AB, sorry, x1 yj. Okay. Not viewable? Can't read it? Okay. I'll keep that in mind. Okay. Yes. So, in general, so any set of probabilities that I can write down on a table like this have to satisfy 3 basic conditions. The first one, and I'm going to try and write this in a general kind of way. So say that I have many parties with many different inputs, then I will have some like AI, BJ, and more inputs for more parties, for XI, YJ, and different inputs for those different parties. This needs to be greater than 0. You also need to have something like these, so normalization, AI, BJ, and all the other inputs, AI, BJ, and XI, YJ. This needs to be equal to 1. And so it's kind of, it's maybe a little bit cumbersome to write this one, but PAI XI is equal to, in general, there's going to be many, we're lucky in this case, there's not too many ways to write this. In general, there will be many, so maybe I should put, there's like a set of these. There's also many of these, actually. Maybe the better way to just say this is for every set of inputs, xi, yj. And then for here, this is going to be, if I want AI, this is just one instance of this. Then I have to sum over everything else, bj. So p, AI, bj, all the other inputs, xi, yj equals, sorry, you can't read those inputs. And basically, I have another set of equalities like this for every input. And now I will try to be as lazy as possible to not write this down. Okay. So b j prime dot PAI BJ prime XI YJ prime, so on and so forth. And then there's more like this. So these are 3 basic properties that no signaling distributions should obey. So let's just look at some examples to see how this works. Okay, so there's a few that are very common. So I have these. So I'm going to be looking again at the SH scenario. It's kind of just the most compact and nicest one to look at. And it gets across all of the main ideas. So when I have a deterministic box, what does that mean? It means that I get a certain set of outcomes with unit probability. So this is the case where, so I'll just write it down. So this is a case where you have this outcome come out with unit probability, or you can also think of these as saying that, let's see now, if this is x0 and this is a0 equals 0, a0 equals 1, b0 equals 0, b, so on and so forth. If you look through all of these, this is the same thing as saying that I get predetermined outcomes with unit probability. So anyway, this is one example of a no signaling distribution. I'm not going to go into that second part. Okay, you can also have, so this is a classical distribution, more general. So, and we have not gotten into what makes this classical versus something else. I'm just giving you examples. Perhaps what I can do is make this a little bit higher and then just use just this column. So if I look at this one, for example, I can put maybe something other than zeros and ones. I can put like 1/2. In fact, this turns out to be a convex combination, and something that I'm going to define later, of two deterministic boxes. It's not a priori clear why you can add up these two different boxes, so we have to make this more precise. From a physics perspective, you want to look at these boxes as resources. They're some sort of physical system. And the reason that you can sort of take convex combinations in an intuitive level is like, I have some sort of machine that prepares one of these boxes and then flips a coin, decides I'm going to pick one of this box or another box like this. And basically, that's the box that Alice and Bob use to do their measurements. And so 50% of the time, the machine is picking this box. 50% of the time, it's picking another one. And so classical correlations are something that you can sort of think of like this in some sense. And then here's another distribution, which looks an awful lot like this one, but is very different. And so this one is going to be non-local. In fact, it's I can give the name. So this is, maybe can't read that. Pescu Roar 1994. And so the box looks like this. So it looks very much like this one. I'm going to put 1/2 on these diagonals. But then I'm going to put zeros here, 1/2, 1/2. So actually, this one, there's going to be something called a no signaling polytope. This is a vertex of it. This is a vertex of it. What that means is it cannot be written as a probabilistic mixture of other points in this set. And this one, in fact, can be. So, but this is a vertex, and you can sort of show yourself that you can sort of prove for yourself that there's no combination. There's 16 boxes like this. No combination of these will ever give you this one. Any questions so far? Is this material familiar, by the way, for most people?
I think we talked about serialization and quantum in class, right?
Yeah, I don't know if it was couched in this sort of a language.
No, so we haven't talked about those.
Yeah, exactly. So that's a good point. So the question is, yeah, so this is not quantum realizable, by the way. Yeah.
Yeah, my point was you can use the inequalities to show that they are not convex hollow fields.
Yes, that's right. Okay. So now we need to do just enough work. I mean, in the physicist sort of tradition, just do enough math to sort of get the basic ideas across and not a single bit more. So I'm just going to loosely say something about this for people who are, because I don't think that in undergrad I'm learning about convex sets in the physics education. So I'm just going to sort of loosely, I'm going to define it, but then I'm going to give a picture which sort of gives the idea that I'm interested in. So subset, and maybe I should demark where I want to go. Subset RD is convex if for any C, then the line given by tx plus 1 minus ty is an element also of C, where t is in the interval 0 to 1. So let's just give a picture. So the idea is the following. Just I'll give you an example. This is not a perfect circle, obviously, but the circle is convex. So if I just take any 2 points here, x and y, the line between them is always going to be contained within the circle. So x and y are in the circle, their line is also in the circle, and if you do this for any choices of x and y, then your set is convex. If you have something that's like this is like a standard sort of, so this x will be inside my set, y is also inside my set, but this is not, so we have yes, no. Okay. So a couple of other things. Another definition, sorry. So given a set of vectors xi, where each xi is an element of Rd. This is real Euclidean space in d dimensions. Then we say that V equals lambda I xi is a convex where, and this part is interesting, so we require that these lambda i's, so what is this? I can think of these xi's, this is a set of vectors. I can of course add vectors together, but this is a particular kind of linear combination where I restrict this to be non-negative, and I restrict the sum of these lambda i's. Oh, what? No, definitely not. Sorry. Equals to 1. So in a physicsy sort of language, if there was some sort of actual interpretation assigned to these x's, you could think of this convex combination as some sort of probabilistic combination of these points. Later on, we're going to be thinking of points in our space as these sorts of distributions. And because I can think of these distributions as points in some real Euclidean space, I can take convex combinations. And that's like preparing a resource that's a probabilistic mixture of different sort of basic resources, which are vertices. Okay. Yes. Okay, 1 second. I just want to square myself up. Something like this looks okay. Okay, so we're going to go further a little bit. Okay, so I'm going to give you the sort of definition that's going to probably not be very illuminating. Then we're going to look at an example and see what a convex polytope is and understand the following theorem. So, which in some sense is like the definition of a polytope. So this is a theorem due to oops. Okay, so the statement is the following. For P, which is a subset of RD, I'm going to use the following, I've seen this somewhere. The following are equivalent, okay. Okay, so the first statement is that pi is a bounded polyhedron. Okay, so we didn't define that, and I'm probably not going to be too precise about it. I'm going to show by pictures what I mean by a bounded polyhedron, and we're just going to leave it at that for now, but we can go into more detail if people have questions. So, I mean, the closest I'll come is the following. It's the solution to a set of linear inequalities. Maybe I should write that last part out because that's important. Inequalities. Okay, the second one. So let's say this is continued from before. The second statement is the following. By the way, maybe I use a different color for this. This is called an H representation because H stands for a half space. So this is where that's coming from. And so the next one, okay, the whole time we should be thinking of, basically, I'll give you the punchline. A polytope can be thought of basically as its flat surfaces, the sides, or as its corners. In a cube, you have 6 flat sides, one for each number on a roll of a dice, but then you also have 8 corners. So this theorem is telling you that if you have an object which is bounded and it's a set of these these flat sides, then it's also the same thing as a convex mixture of its vertices. Okay. So 2. So it's the So here I have a couple of things to sort of explain just a little bit. Here, xi is a set of, it's a finite, so xi is a finite set, finite point set, maybe easiest point set. Second thing, and I'm just going to rip this from Wikipedia. This can be more precisely defined, but just the intuitive picture of what is this. So convex, so the convex of something is in some sense, quote, the smallest convex set, containing those points okay, and so more colors. So I guess this one, for more obvious reasons, is the vrep, because typically at least some subset of these points here are going to be vertices of your polytope. Not all of them, right? Because if I take 3 points, or maybe I do it like this. Say I take 3 points, maybe you can't see this. I'll write them like this. And these are all on a line. So I could take these 3 points, and the convex hull of these is going to be a straight line through them. 2 of them will be vertices, but the third one is not. So it just means that a subset of these will probably be, or the subset of these will definitely be vertices, but not all. Okay, so now an example. So let's look at the cube. Okay, so what I want to go through is this definition and this definition. Okay, so let's look at the H side. Well, so let's also define the following. Let's set a system of coordinates just to make things easy for us. Let's take the center of the cube to be the origin. Something like this, so that this is the first quadrant. So I have, okay, so this bounding wall is the same thing as saying, if I take this to be x, y, and z, then I want x to be greater than -1. I'm going to just take the cube to have be 1 from each side. It's greater than -1, but less than +1. And I also do this for y and z. So y and z. Okay, I can just, it's easy enough to just do it in this case. So I can just write this cube as being defined like this. I could also write the cube just in terms of, I give you a set of points. Here, this point right here is which one? This is the positive quadrant. So this is 1, 1, 1, in saying that the coordinates are equal to 1 in every spot. And then there's 8 like that. So when I look at the V representation, I have any given vertex say ijk, this is too small, vijk. I'm using the vectors in terms of their components here, the way that I'm writing this. So it's -1 to the I. Sorry, I don't need to write anything else. I just need to write this. Where I, j, and k, I'll write that in a second. -1 to the j, -1 to the k, where I, j, k are either 0 or 1. So you can check, Hoyu, we can see this, right?
Yeah, but a little bit picture would be.
Bigger is better. Okay, that's okay. So yeah, you can check for yourself that this is all. How many options do I have here? I have 2 for each, so this is 2 to the third. That gives me the eight vertices that I'm looking for. In fact, all cubes you can just generalize like this. They have 2 to the number of dimension vertices, and they're all just going to be plus and minus 1 like this. Yes. Okay, so now let's bring it back down to earth a little and talk about, I guess, the physics stuff. Sorry. Okay, so what time is it? I can't really read that. Oh, no, I have it here, 3:20. Okay. Okay, so remember that we had these properties. Do I still have them up here? I don't think so, right? So I have these properties that each of the, I'm just gonna, I don't want to rewrite the whole thing too much. So I have that this is non-negative. There's the 3 n's, right? Non-negative, normalization, equals 1, and then also no signaling. So we have the 3 n conditions, and I want to just show you that these form a polytope. And I just write no signaling here. No need to. This is do I need this? Let's leave it for a second. So the following thing that we want to say is let's just define NS. This is just the symbol that I'm going to use, is the set of no signaling distributions for a given. Okay, so what are the properties of this set have to be? So from 1, what we sort of automatically see here is that we kind of have inequalities. So we're already looking at something like this H representation. And in fact, so this is something that I should have mentioned. So when I look at this theorem tells me that there is an equivalence between these two things. It doesn't tell me how to go between those two descriptions. And in general, that's a very hard problem. So I'm given an H, but I really kind of want to know what the distributions are that are allowed. So I have to go from here to there. And in a lot of these problems, this is what we're interested in. There's an opposite problem. If I'm given the vertices, find the faces of the polytope. Can anyone think of a physics application where you're going from the vertices to the facets, to the faces of the shape? In no signaling, we're always going from H to V pretty much. But then there's also, yeah, if you're looking for the Bell polytope, right? So what is the Bell polytope? I first give you a set of possible hidden variable models, basically deterministic distributions. And so I'm giving you, those are going to be vertices. And then I'm asking, okay, well, what is the H description? And the Bell inequalities are precisely facets of that polytope. So it's going from here to there. And both of them, it's the same problem. And they're both equally difficult, essentially up to like polynomial time or something. Okay, so from one, we know that NS is a polyhedron. Okay, so by that, I just mean that there's a set of inequalities and that the no signaling distributions fall within this set of inequalities. So a picture would be something like this. Picture that this is R3, and this is the positive quadrant of R3. So if I just had inequalities that said x greater than 0, y greater than 0, z greater than 0, it would just be the whole the whole positive quadrant of this. It's a polyhedron because it's not bounded, right? So it's convex, it has all these properties. So the difference between a polytope and a polyhedron is just that polytope is bounded. But here, just based on the first property, you just know that it's convex and that it has these flat sides, so it's a polyhedron. From two, you get the following thing, that NS is a bounded polyhedron or just and how do you see this? You see this because when I'm looking here and each of these is positive and they add up to 1, that means that that at for any given distribution, the most that this could ever be is up to 1. So you have that PAB is, so it's bounded, it's a polytope. So the third thing, which maybe I'll just say symbolically, is the following, that if I intersect a polytope with another flat sort of like a plane, then I just get another polytope. So if I take, maybe make this bigger, sorry. So if I have the cube and I just cut the cube in half, I just take a slice of it, that gives me a square. So that will just give me a square, which is also its own kind of polytope in 2 dimensions. So the reason that that's important is because we already know from these two that NS is a polytope. These no signaling conditions, what are they? Maybe I don't have them anymore, but they're just the equations of a plane. Maybe I'll give an example. So for the CH-SH scenario, you had something like one of the equations, just a particular example of them would be like P0000 plus P0100 equals P001 plus P101. So this is the equation of a plane. in the sense that you have P0000 plus this one minus this one minus this one equals 0. This is the equation. So you go from this one, and that gives you also a polytope. So in order to save some time, I think I can just go to this. So I went a little bit off script in the sense that this paper was about finding vertices, but it was also about converting resources. Given in lieu of the things that Aziz will talk about next week and other topics in the course, I think that this connection just being made between going from the distributions to the notion of polytope, that this is something that could be useful conceptually just going forward. So I just decided to take, for pedagogical reasons, a little bit more time with this. So our goal is essentially that we are given a polytope in a particular representation. We want to find yeah, so comment. This is hard. And in fact, there's a more actual technical way of saying this. There's a result that says that in general, finding going from the facets to the vertices for these no signaling type problems is NP complete. So some people who took Jian's class the other day, we understand what NP complete is. So I'm going to use one definition. Actually, I'll come back to this in a second, but this is a result due to perhaps Igor's countryman, I don't know, Pitowski, just guessing. Let's see. Okay, so we want to find the vertices. So first we should probably define what that is in a more or less concrete way. So let's call this a fact. And it's just, so a vertex, so a point. So this is sort of more of an intuitive definition. A point P, actually they're both pretty intuitive, but a point P element of NS is a vertex if it cannot be written as a, and I'm just going to write convex, yeah, is a convex combination of other points in NS. Okay, that's kind of nice. But so actually to do a calculation, I think that this is maybe not the most efficient representation of what a vertex is. So there's this other definition or fact. It's just a basic fact from polytope theory, which is that if we think of our polytope as being in some d-dimensional Euclidean space, P element of NS is a vertex And let's see. Can you see this HOU at the bottom, or it's okay? Which subscript? But here on this page? Okay. If is a vertex, if and only if it is the unique this probably won't unique solution to D inequalities. So if you guys will indulge me, I will continue from over here. Okay. Okay, yeah, I can fit it there. That's fine. Maybe I should just give myself this sort of thing. So solution to D. So I will continue solution to D inequalities satisfied with equality. Equality for all. Only for D of them, actually. So let's just do an example to see what that looks like. Oh, and I already have one here. I'll just take a look at this so I will avoid doing more work. So if I look at this vertex right here, so I have 6 inequalities. Can anyone tell me which 6 inequalities? So this is a vertex, we know. Which 6 inequalities, this is a polytope in R3. Therefore, I only need to satisfy 3 of these inequalities with equality. What does that mean? I have to take, this is 6, right? 1, 2, 3, 4, 5, 6. I have to take some linearly independent, by which I mean I can't satisfy both of these at the same time, or both of these. So there's some additional criterion. That's what I mean when I say unique. So that's part of the definition there. So if I want to say, okay, I have this vertex, this one is the unique solution to x less than 1, y less than 1, z less than 1. And in precisely, yeah, I'm taking, so yeah, that's what I was going to say. These are the inequalities I want to look at, and I want to set them equal to precisely these bounds. So I take these 3 inequalities and I set them equal to 1. So yeah, I will just leave it at that so I don't take too much more time. But you see how that's a sort of intuitive thing. Of course, the cube is very simple, though. In general, there's this problem of there's many choices that you could have for how to actually look at the possible inequalities that are satisfied with equality. It's kind of difficult. So let's look at sort of an actual application of this. Okay. So I want to look at the CH-SH scenario. So I want to make the following claim. Proposition. I don't know if I defined it as such. The Popescu-Rohrlich box that I introduced before, the PR box is a vertex of NS CH-SH. So here is the proof. This is not going to be a proof that's particularly constructive. So I wanted to make this, come back to this point. MP complete, one definition of this is the following, that, intuitively, what is it? If I give you a solution, you can check very quickly that the solution is indeed correct. But in general, finding that solution in the first place could be very difficult. So what the relevance here is, I already know, I don't have it here, I already know what the PR box looks like. I know where the zeros are. I'm just going to put the zeros in and show that it indeed gives me a unique solution. That's easy to do. It takes me just a couple of steps. In order to find that from the space of all possible distributions that this is a vertex, that problem is harder. So the first thing we have to do is, what is the dimension of our polytope? Here it's easy to see. So let delta be the dimension of NS. So how do I compute this? I think I still have some stuff I can use. Over here, basically, I can start off in a dimension that's as many as the probabilities that I have. So we're going to have, in the CHSH case, four boxes of 4. There's going to be 16. So I can just write this here. So for CHSH, there's 16. How many normalization constraints? Every time I have a constraint, it means that one of the variables depends on the other. So I go to a space of lower dimension. Here there's going to be 4 of them. And here, how many no signaling distributions? Okay, for here, it's going to be better that I write down the box. But the answer is, for CHSH, there's 4, but it's not immediately obvious. So it's going to be 16 minus 4 minus 4. Even I can do this. This one is going to be 8. So we have that our polytope is inside, it's a subset, I'll just use this, of R8. So okay. Any questions this far? Okay, it seems like people are nodding. So let me just draw the box. So just to give us an idea of what's going on here. I'm not going to put all the bells and whistles. Let's just leave it like this for a second. And so I just want to talk about the no signaling conditions for one moment. In general, Alice is going to have her outcome A for this measurement setting. So maybe I can put it just here. This is x0. And here we have A0 equals 0. So there's going to be a no signaling condition here, because when Alice does this measurement and gets the outcome A, it should not depend on whether Bob did Y0 or whether Bob did Y1. So it's going to be, I'm going to do this number plus this number equals this number plus this number. Now, there's an easy mistake to make where you might say, okay, now I have to do the same thing here. You don't do that. I mean, you can, but it's redundant. Why? Because say I did it, maybe use a different color. This is not going to be a good way of counting the number of no signaling constraints. If I did do this one and this one, and this one and this one, okay, and say that these two are now equal to each other. But if I add these two no signaling conditions together, I get these two plus this two equals this two plus this two, which is the normalization condition. So I can either have the two no signaling, but no normalization, or I could have one no signaling plus normalization. Either way, I can't have all of them. So that's not good. But I do have, but I do have this, in addition to this one. And okay, I'll get that. And then I do have, for Bob's settings, I have this and this, as well as this and this. So 1, 2, 3, 4. I don't know why I drew it like that. That's not consistent. Okay, so now to show that the PR box is a vertex, let's just get rid of these very quickly. Okay, so the PR box, if you remember, I'm not going to put down the 1/2s. I'm just going to put where the zeros are, right? Because, yeah, sorry, I keep going back and forth. Here, the inequalities to be satisfied with equality are precisely these. That means I have to set 8 probabilities equal to 0, and then I should have a unique solution for my probability for my no signaling distribution. So where were the zeros? They were here, 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 and then here and here. Okay, so let's just put a parameter p here. Then here I'm going to have 1 minus p because it has to add up to 1. So I'm going to use a notation. 1 minus p is defined as p bar. So here I have p bar. Okay, but already no signaling tells me that this has to be p. And then no signaling tells me that this has to be p bar. Similarly, here, here, and then I get here p bar p. Does anyone notice, is this unique? Somebody knows, he's not saying. I thought that you nodded yes, no? Oh, okay. You nodded knowingly, okay. Yeah, so where is the uniqueness come from? Here I have, after a string of no signaling conditions, I go from here to there, and then, oh, p bar equals p. But there's only one solution to this. P bar equals p equals, okay, I can just do out the whole thing. This implies 1 minus p equals p. Solve for p, even I can do this one. P equals 1/2. Okay, yeah, so this is the idea. If I gave you the distribution of zeros, it's easy. The hard part is finding that these should be the zeros that give me a vertex in the first place. You have to just essentially keep trying different stuff. Yeah, sorry, I do want to say, just to emphasize this point very quickly, I want to emphasize this point. Say I did this one, 0, 0, 0, 0, 0, 0, 0, 0, and then I put some other stuff here. I have 8 zeros here. Should this be a vertex? Clearly, because I'm talking about it, it probably is not. P bar, Q, Q bar. Yeah, so there's 8 zeros. That doesn't mean anything. Why? Because these are related by no signaling. This equals to this identically. There's only, in these 4 parameters, they're connected by a no signaling, oops, this one, so that this is actually only 3 independent zeros in some sense. And so this one is also 3. So what does that mean? If I'm in dimension 8, but I only have 6 actually independent zeros, then I'm left over with 2 parameters. 8 minus 6 equals 2 parameters. That's, and so if they,
you add that two, you get deterministic, right?
yeah, exactly. So this one is not good. Yeah, so now if I say I have to pick somewhere to put a 0, I have to pick one of these. Okay, I picked this one. This is 0. Okay, then this is 0. Then this is 1. And this is 1. And now I'm left only just with choosing. I can only just choose. I have to pick one more 0. And it's either I have 1s and 0s. This is the only choice. I seem to refer to this one quite a bit, so I will leave this here. And I don't think I have, I don't want to take too much time because you guys are Friday afternoon. You're kind enough to join us. I think this is very nice. You guys are truly nerds. So yes, I wanted to, so here's the main, so I want to just set up some notation, but the main theorem of this paper, which I doubt I'll be able to prove, maybe I'll be able to sketch it just very quickly. First, I want to just define a notation. So when I say 2 dxia d formerly, I had a notation, recall, of 2, 2, 2. This meant the number of parties, this meant the number of measurement inputs, and this was the number of outcomes. And I could write it very nice like this because the number of outcomes per measurement, per party, were always the same. But in this paper, they consider the situation, and I'm just gonna, it's easier to draw a picture, where the outcomes of each measurement setting could be different. So for example, if you have something like, maybe you have like, this is small. So maybe there's like, this one is, I'll just write the outcomes, 0 and 1, 0 and 1 for both Alice and Bob on their measurement setting X. So this is for X0, but maybe for, sorry, X1, you have like 0, 1, make this more obvious, to D something, dx1. I guess dx1 minus 1 to be consistent. And then similarly, like this, you can have just different numbers, and then this is going to be how many probabilities are in here. Just it's this number times that number. So for, yeah, maybe if I pick something concrete like 4, just to 0, 1, 2, 3, and here I pick just like 0, 1, 2. How many probabilities in here? There's 4. How many in here? There's 2 times 4. There's 8 in here. There's 6 in here. And then this is 12 or something. So it's something much more complicated. And so based on this, they have the following theorem. So for this scenario, what was my notation? dA I dyj. So for this scenario, up to symmetry, which I'll try to talk about in a second, the non-local vertices are so it's 1 over some k, maybe make this a little bigger, such that, I don't think I can redo this. So such that B minus A mod K equals xi yj. This is just multiplying the input settings, so sorry. And then 0, oh, sorry. There's one more piece where A and B are from 0 to k minus 1. And then it's 0 otherwise. And so this is for every k element of 2. This 2 is important. If you start from 1, it doesn't work, I realized. To min of d a x I d b y j. Okay, so maybe the first thing to do is to just check that this works. So I will just do a quick. Let me do a quick check on something that's simple. So if we do 222, then here just.
One question.
Sorry, yeah, maybe I should explain this a little bit more. Go ahead.
And then you get
Yeah, so I think it's going to be more easy to see when I do an example. But what it is for, so k could be anywhere from 2 to the minimum of these. So for every k that satisfies this, so if the minimum is 3, then it's for 2 and 3. Yeah.
And then you get.
Yeah, and then this is the and then.
This is all the vertices?
Yeah, always like this. By the way, the stabilizer for all of them. Yeah, exactly. Okay. So yeah, they all have this form. By the way, so if I do for the 222 scenario, it's P A B X I Y J is equal to it's 1/2. Basically, it's the same thing as saying that A plus B equals xi yj. Why? Because when mod 2, negative is positive because adding 1 is like subtracting 1. Anyway, but this is a form that people know. That's why I write it like this. People have seen this before. So this reduces, this you can do as a assign to the, as a homework project. Yeah, check that this is indeed the PR box. Okay, another check, one that's a little bit less trivial. Except my director says that I should have a line like this here to make sure that I'm not being cut off. Another check is the following scenario. 223. And in this case, we can have k can be an element of 2 or 3. And so I will write down the expressions for both. And I will also, I do want to write down what the distributions look like. Maybe it's a good idea to write down the picture first. So for 2, hopefully this will be legible because there's a lot more probabilities, right, in this one. In the case where d equals 3, in each cell you have 3 times 3 numbers of probabilities, so there's 9 in each. So here you have I'm fixing d to be 3, the same for both, and the k equals 2 vertex is of the form 1/2, 1/2, 0. And I think Aziz probably sees where this is going. In fact, maybe more than just Aziz. Zero. Huh.
Maybe
Okay.
you have to change one.
Yeah, I did. Yeah. Sorry, it's hard to see. It's diagonal, 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 off diagonal. So what is this? Do I have it here? Yeah, this is PR box, right? Except, so actually this is it should have been a lemma, but they don't put it as a lemma in the paper, which is the following. They see anytime there's a row or column of zeros, they think of this as being a vertex in a smaller polytope. It's like you're getting rid of this outcome because it never happens. And then, so you can always just consider anytime there's zeros like this, you can look at the smaller polytope and then lift it up to the bigger polytope and always put zeros here, and this is still a vertex. So there's a sort of, they don't say this very precisely, and I was a little bit surprised that it works, but it does seem to work. That you just put the zeros here again, and then this is a vertex. Anyway, so this is for k equals 2, k equals 3, this seems like it's going to be too small, sorry. Okay, and so this one also, I'm just gonna not put all the zeros, or I'll just put dots where the zeros are. And sorry. Yeah, so I'll explain. So diagonals, so this is also going to be diagonals on the, 1/3 on the diagonal, 1/3 on the diagonal, and then 1, 2, 1, 2, 3, 4. Like this. So this is also a vertex. The basic construction that they use to prove this sort of theorem is that, okay, I'm almost out of time, so I'll just talk about it right now in this sort of simple example. In general, you could have something very complicated like this here, all these different things, but so when you carry out the dimensional analysis of how many probabilities are here, how many no signaling, how many whatever, what they want to do is they always want to get rid of the situations where they have zeros in an entire row or an entire column. They want to consider that case separately. So anytime there's too many zeros in a row or column, consider that case separately. And essentially, they always consider the cases that come down to squares. Just, it's 2 by 2, but also inside the squares, it's like 4 or 9 or 16 or something. So they always reduce everything to the case where this D is the same for both. And they want to make sure that there's no zeros on any rows or columns. And then they can always consider those cases later by lifting and adding the zeros. What did I want to say very quickly? Yeah, so if you look at the construction of the zeros here, for example, you want to make sure that there's only one way of making sure that you write the zeros so that there's not 3 in a row. It's like this and like this, basically. So let me write this down. So this is P, and now I think that I've lost my spot. Okay, anyway, I think that this is, so for the k equals 2 case, it's the same thing as this pretty much. So I'm not going to write it down again. So for k equals 3, sorry, okay, so k equals 3, 1/3 b minus a. This is just me rewriting the equation, so it's not really necessary. 3 equals xi yj, a, b, 0, 1, 2, and 0 otherwise. Okay, I think that that's the basic idea. I think checking it, you get the basic principle, which is that you start from this complicated thing. It's going to turn out in many of the cases that you have too many zeros, and then you're going to get a 0 in a row or column. You get rid of those. You don't consider this case. You get rid of it, and you only consider the cases where there's no zeros in any row or column, and then it's going to look something like this. Either maybe they're on the diagonal or they're in this sort of zigzag pattern, and that's the construction technique essentially. And then there's another symmetry part which I didn't get into probably sufficiently. Maybe we'll discuss it another time, or maybe Aziz will mention something about it. Okay, I think that that's it. I don't know which frame I'm in, but okay. Okay, that's it. Thanks for coming, guys. Aziz will talk about sheaf theory. That sounds very fancy, but basically it's dealing with this sort of stuff, but maybe making it a little bit more elegant. And I don't think it's too hard to follow even for a physicist, so it's okay. And Aziz knows it very well, so I think you should come next week and listen to him talk about it.